Okay, so I hope everybody found where the restrooms were, found where the coffee was, had an opportunity to talk to some of the students and the labs that are set up there. Note that we will have different labs that will be rotating in and out across these next 2 days. So many of you who have attended in the past know that we always we try to send out a survey afterwards, sometimes formally, sometimes informally. And the feedback consistently the last 2 years has been, we'd love to continue to hear more about the research that's going on at Purdue. So if you take a look, if you've been here in the past, you take a look at the agenda, we have slated a whole bunch more speakers, many of them for lightning talks to give you a quick taste of the research that's going on in his or her laboratory. But give you an opportunity then maybe seek them out during the break time. But this is our opportunity to have our very first technical talk. One of the 163 Purdue affiliated faculty who are conducting cyber systems oriented research. So let me lay the groundwork there. We are all known as cybersecurity. We talk about that, but CERIAS defines its cybersecurity research areas as cyber physical systems with a focus on security, privacy, resiliency, autonomous systems, trusted microelectronics, and trustworthy AI. So we have a very broad definition, and we're going to touch on most of these over the next 2 days. So it's my pleasure now to introduce our first lightning talk presenter, Professor Jing Gao. Jing is associate professor in Purdue's Electrical and Computer Engineering Department. Welcome.
Thank you. Yeah, thanks for the introduction. So I'm Jing Gao. I'm associate professor in ECE. So actually, my major research area is data mining and machine learning. So in our group, we develop data mining, machine learning solutions for applications. But as you know, the resilience, the robustness of these models is very important. So therefore, one of our research directions is exploring that perspective. So today I will talk about our work on data poisoning attacks. So let's start with just the basic procedure of machine learning system for classification. So suppose we want to classify an image into a category based on the object it contains. So suppose we extract some features from the images. So that's our X. And then the class label is Y. And suppose we have a large collection of such X, Y pairs. So that's our training set. And then from the training set, we can derive a classifier, or we say a model F. So its parameter is theta, which derives the relationship between X and Y. And then once we have that model during the testing phase, we can give that image into that model, and then the model can predict which class it belongs to. So such model has wide applications, right? So we can derive classification models for stop sign detection, for face recognition, for like predicting environment in this autonomous driving. But as we can see from the examples here, attackers can exploit the vulnerabilities of these models to manipulate the output. So for example, we can like add some patches to the stop sign to fool the stop sign detection system. So we can like add glasses to fool this face recognition. And then in this later with autonomous driving, so we can like make some changes to the sensor data so that the prediction will be falsified. So therefore, exploring these attacks can help us better understand the vulnerabilities of our models. So therefore, studying these attacks becomes a very important subfield in machine learning and security research. So people exploit these attacks from many different perspectives. So here I just try to categorize these attacks. So first of all, the attackers can launch attacks at different phases. So for example, we can like change the test sample to evade detection. So that is attacks at the testing phase. So usually people call it evasion attacks. And then sometimes the attackers can inject some triggering patterns during the training phase, and then add the similar triggering patterns into the test samples. So this is called backdoor attacks. So this involves both training and testing phase. And then people study also this data poisoning attacks. So this is only at the training phase. So during the training phase, so we inject some adversarial samples into the training data, or we change the data, we modify data, and with the goal of manipulating the output at the testing phase. So this is the data poisoning attacks that we will discuss later. And also people can assume that the attacker may have different levels of knowledge. So maybe the attacker has full knowledge about the model, so that is white box attacks. If the attacker has no knowledge about the model, that is black box attacks. And recently, people also study this gray box attacks, where the attackers has partial knowledge about the model. And then these two are mainly about the data poisoning attacks. So for example, at first, people find that if we just inject this misaligned XY pairs into the training set, so we can have very successful data poisoning attacks. But the limit is that such mislabeled pairs are very easy to detect. So therefore, later people mainly focus on so-called clean label attacks, so in which we only add small unnoticeable perturbations. So such attacks are much harder to detect. And then for in terms of attack goals, so our goal is to manipulate the training data to affect the outputs at the testing phase, but we can still focus on particular target samples. So for such attacks, people usually call targeted attacks or subpopulation attacks. And then some other lines of work focus on degrade the classification performance in general. So that is availability attacks. Okay, so our focus, particularly in this talk, so we will talk about clean label data poisoning attacks. So that is the training phase attack. And we focus on the more difficult, more challenging clean label attacks. So basically, we want to add small perturbations to training data in order to manipulate the output of the machine learning model. So here we have an example people usually use to demonstrate how unnoticeable the noise, the perturbations we add to the training data. And then we will talk about both white box and black box attacks. And then the attack goals vary based on different tasks. Okay, so let me still just summarize data poisoning attacks. So let's start with the traditional machine learning. So we have training data, we train the model, and then we use the model to make predictions on the test samples. But for data poisoning attack, so the idea is to add poison data into the training data. And now we will derive a poison model during this model training phase. So the model will be trained on both the original training data and the poison data. And then now when we use the model on the test samples, we will get falsified prediction. So So the focus of our work is actually on this, how to craft these adversarial samples to be added to the training data. So now we place ourselves in an attacker's position. So how to best design attack, how to best craft adversarial samples to achieve the attack goal. So that's our focus. Okay, so then to talk about that, I will discuss from two perspectives, white box attacks and black box attacks. And then in each of them, so I will first talk about the general strategies people use, and then use the example from our work to illustrate how we achieve that. So let's start with white box attacks. So here we basically assume that the attacker has full knowledge about the model. So both the model architecture, both the parameters, so we know everything about the model. So then the general strategy people use to craft adversarial samples in this case is we can formulate the task as a bi-level optimization problem. So the upper level is actually the attack goal. So we want to craft the adversarial samples in the way that we achieve the attack goal, but we have some constraints. So we can't inject too many samples. So the sample should look realistic. So that's the upper level objective. And the lower level objective is basically once we inject these adversarial samples into the training set, we need to like retrain the model. So we need to get the training, the training phase will actually derive the model parameters now based on both the clean data and the poison data. So the lower level usually involves this minimizing the training loss on both clean and poison data. And then to solve this bi-level optimization problem, at first when people start working at simple classifiers, usually involves convex functions, so they can get nice analytic solutions. But later when we like start the attacks on, for example, deep neural networks, so the function is no longer convex, so we need to seek approximate solutions. So now I will start discuss our work for white box attacks. So I will use the examples of this outcome interpretation. So again, if we look at this machine learning model, so suppose we train a machine learning model or classification model. So we have an input image, which is a dog image, and then feed into this machine learning model so it can output that this is a dog, right? But in many applications, people are not satisfied about just receiving a prediction. So they want to understand why this particular prediction is made. So therefore, in machine learning community, people have been studying this interpretable machine learning model. So one way to interpret the result is to add an interpreter based on the machine learning model that can tell us why this particular prediction is made. So in this example, we can see that we use this so-called saliency map as the interpreter. So it basically highlights the regions which is most relevant to the prediction. So now our goal is actually to attack this interpreter, but we assume we have full knowledge about the model. Okay. Oh, sorry. Okay, so just to summarize, so we want to manipulate the specific target samples interpretation results with their classification results unchanged. So that's our attack goal. So suppose we have some target interpretation region. So we want to drag the interpretation toward that target. But during this time, we want to inject some unnoticeable changes. So the classification results should not change. So the approach we use, so we basically add adversarial samples into the training set. And then here the attacker knows the architecture parameters of both interpreter and the machine learning model. So here we focus on the saliency map as the way of the interpreter. So basically the interpreter output is a function. So this depends on the data, depends on the model, F, and depends on the parameter. So it outputs scores over the feature space to indicate the importance of the feature with respect to the classification results. So once we have such scores, we can actually visualize to basically illustrate where it's most related to the prediction. So some ways, some example models that can derive such saliency map or the scoring function. So for example, people use this back propagation guided interpreter. So the score is derived by this gradient magnitude, or people use representation guided interpreter. So the score is derived based on some intermediate layers of the deep neural networks. Okay, so here is our bi-level optimization formulation. So basically we use this GC to integrate the manipulated interpretation. So G is the target interpretation. So T is the target sample and P is adversarial sample. So we use target sample as the base to perturb a little bit to generate the adversarial sample. And then we have the collection of clean data. So this is the XCSP. So that's the value, feature values, and the class label. And then we have the set of adversarial samples as well. And then we can look at the optimization formulation here is basically the lower objective is to find the model parameters that minimize training loss on both clean adversarial data. And then the upper level basically capture our attack goal. So we want to craft adversarial samples such that the attack goal is achieved, which is to make the interpretation to be close to the target. But at the same time, we want the perturbation to be small and unnoticeable. So limited perturbation, and we also want to maintain the classification result. And then this is not a convex function, so we use iterative learning to solve this problem. So the step 1 and step 2 basically work on the upper level optimization. So we first derive the ideal parameter update that can decrease the upper level objective function. And then correspondingly, we craft the adversarial samples that can manipulate model parameters toward that direction. In this step, we basically work on the lower level optimization. So we update the model parameter using the lower level objective function. And then during this process, we found that these ensemble techniques can help stabilize the solution, so make it have better performance. So basically, we initialize the models using different initialization. Okay, and then we try to assemble them during this step 1 and step 2. Okay. So basically that's the white box. I still have the black box, but due to the time limit, I will just try to wrap up, make it quick. So the black box attacks, so the key strategies people use to black box attacks is basically this model simulator. So that plays a very important role because in black box attacks, we have no knowledge about the model, right? But in order to train very successful adversarial attack, we need to have some interactions with the model. So therefore, usually people develop this model simulator to simulate the behavior of the victim model. So this influence function also is actually maybe not restricted to black box attacks. So people sometimes use in white box attack as well. But the key is to estimate the influence of the adversarial samples on the attack goal to avoid the costly retraining of the model. So I guess I will just like show the example and that's it, right? So for black box attack, so what we focus on is this next item recommendation. So this is actually a very popular task in on-line e-commerce website. So basically is given the sequences of the sequence of users previously accessed items. So we want to output this top K recommendations. So I think I will just skip this. Yes.
Go ahead for 2 or 3 more minutes.
Okay.
But if I can have the panelists for the next panel come on up, and that way we're best use of our time. So if you're a moderator or panelist for the next panel, please start your way up here. Jim, go ahead. And
I will just wrap it up. So I'll mainly introduce this framework we have. So we have, suppose we have this online platform, we have black box recommender, and this is the framework we use to launch this data poisoning attack. So it mainly consists of those key components, this recommender simulator. So this part is the influence estimation part. And then based on those, so we will develop this adversarial sample generator. Okay. So that's the, so basically we will just design our attacks based on these modules. So I think I will just skip those. So basically for the recommender simulator, so we want to like make it have consistent results with black box recommender. outcome simulator just to simulate the influence, estimate the influence of the adversarial samples on this recommender simulator. And then for adversarial sample generator, so we formulate it as a Markov decision process. Okay, so basically just show that we can launch effective attacks. Okay, so summary. So basically we work on data poisoning attacks. Our group works on data poisoning attacks. And then there are some works I didn't have chance to introduce. So we also work on this data poisoning attacks towards knowledge graph embedding of fair machine learning. And another important research direction in our group is this trustworthiness on ML models. So we work on this factual correctness evaluation. So one of my students is working on this evaluating the correctness of the answers from LLM, the entries in knowledge graphs, and then we do truth discovery from multi-source conflicting information. We do fake news detection from social media, and some other aspects we work on like fairness, privacy preserving, federated learning, and then we also work on this machine learning when we have developed machine learning models when we have limited resources like memory, quick inference, limited in-domain data. And we also work on multi-source, multi-model data analytics. So if you're interested in any of these topics, I'd be happy to chat offline.
Wonderful. Thank you so much.